Good morning, everyone. So last time we were ending with this picture here and a demonstration on liquid oxygen, on how oxygen was being pulled into a magnetic field in a way that we wouldn't have expected. If we were, again, just kind of looking at the Lewis structure of oxygen, we were kind of thinking all these electrons, according to the Lewis structure, appeared to be spin paired. And we're seeing oxygen was actually paramagnetic, though, that it was being drawn into the magnetic field. So one or more unpaired electrons in a molecule makes a molecule be paramagnetic. That means it's going to be drawn into a magnetic field. If the molecule had all spin paired electrons, then it would be diamagnetic and wouldn't be drawn into a magnetic field. And so an example of a paramagnetic molecule we saw here was O2. An example of a diamagnetic molecule would be something like nitrogen. So we saw liquid nitrogen over the magnet wasn't being drawn in the same way to the magnetic field. And so what we want to do here is take a look at a theory called molecular orbital theory to try to understand this property of oxygen a little bit better. And so if we extend past, we looked at hydrogen and helium last time for H2 and helium, and they kind of look like these diagrams here, where for H2 we were putting in 2 electrons, and then for helium-2 we're putting in 4 electrons into the sigma 1s for hydrogen, then having to use the antibonding orbital for helium-2. So for helium-2, that wasn't forming a molecule because if you recall, it had a 0 bond order. So here we're looking at dilithium, which again isn't likely a compound we're going to encounter in this diatomic form, but it's just an idea of what would its orbitals look like if it were to pair up the 2 lithiums with each other. And so we have the 1s orbitals bonding and anti-bonding, and then the 2s probably more bonding, so more down and more up for the 2s orbitals because these orbitals are simply bigger. So we're imagining lithium for one atom has a 1s orbital, the other lithium has a 1s orbital, and then we have the bigger 2s orbital. And so we're probably going to get better overlap. So if we're thinking of overlap of orbitals, the bigger orbitals can overlap better. That's going to give us a bigger bonding character when we move downward in our diagram. In fact, this might be a little too much down and up for the 1s. You might think the bonding and anti-bonding contribution for a core orbital probably isn't going to be very substantial. So here we see a sigma 2s, and then we have the anti-bonding 2s for lithium-2 that wouldn't be used in the process for lithium-2. So if we were to calculate the bond order of lithium-2, if you recall, it's 1/2 the number of bonding electrons, and so our bonding electrons are these 2 plus those 2, because they're in the non-star orbitals. So we have 4 electrons in bonding orbitals, and then we have 2 electrons in anti-bonding orbitals. So we have our bonding electrons, and then our non-bonding, or actually our anti-bonding electrons. We have our star, our anti-bonding electrons, and then our non-star bonding electrons. So the net bond is the bonding minus the anti-bonding electrons, cut it in half because we're counting electrons, we want to go electron pairs, and so that gives us a bond order of 1. So we have a single bond, is what this would mean. So we have a single bond between the 2 lithiums. And I think that's what we would expect. We expect lithium with 1 valence electron, the other lithium with 1 valence, probably forming a single bond between the 2 atoms. Okay, now if we wanted to extend, I think the next slide will be beryllium-2. If we just kind of extend along the diatomic molecules in the second row of the periodic table, beryllium-2 is going to have to use the antibonding orbital. It's going to be like helium-2. It's going to have no net bond in a diatomic molecule between 2 berylliums. Right, perhaps that wasn't on the next slide. I thought it was on the next slide. So for beryllium-2, if we want to imagine what beryllium-2 would look like, we could do like an electron diagram for its molecular orbital. So we'd have a sigma 1s2, meaning we have 2 electrons in a sigma 1s orbital. We'd have 2 electrons in the sigma star 1s orbital. We'd have 2 electrons in the sigma 2s, and then we'd have 2 electrons in the sigma star 2s. And so, of course, we'd have 4 bonding, 4 anti-bonding electrons. So for beryllium-2, our bond order would be a half and then 4 minus 4. So we'd expect beryllium-2 as a diatomic molecule to be unstable, that it wouldn't form an actual bond between those atoms. Now let's think a little bit as we extend upward into p orbitals that can overlap as we get past beryllium into boron, carbon, and then closer towards molecules that exist as diatomic molecules naturally, like N2, O2, F2, et cetera, that we have to think about how the p orbitals will overlap. And so one of the things that this diagram, I think it's a little confusing the first time you glance at it, is the thought that we have a few things going on at the same time. One, we have orbitals at different size, like 2s versus 2p. The 2p orbital is a little bit bigger than the 2s, and then they have a different shape. And then they're also oriented in a particular fashion. Like we're imagining a molecule maybe like 2 boron atoms, let's say, where boron, we might be imagining, has access to its 2s shell orbitals that can overlap. And so the same type of overlap we just saw. And then we would have the p orbitals on boron that would want to align with each other in this fashion here. So we have the p orbitals that are straight up and down, the orbitals pointed straight at each other. So we have orbitals pointing this way, orbitals that are more vertical, and then we have a third orbital sticking straight out of the page, which I think for now I'm going to neglect, but if you think of this orbital here, we have a second set of orbitals that looks just like that. And so when we think about our orbitals, we have our end-on-end overlap. And so the key is recognizing that the center of the p orbital is the nuclei of the 2 atoms. And so we have the nuclei of the 2 atoms. And so we get this type of overlap here. And this is sigma overlap, meaning that looks like a sigma bond from valence bond theory. So that's the bonding is symmetrical about the bond axis. And so then we just have the electrons meeting in the center for our bonding orbital, and then our anti-bonding orbital puts the electrons far away from each other. And maybe at this point it's worthwhile just to remind ourselves when we looked at like hydrogen, for example, and we saw that hydrogen, we had an orbital go down for our sigma 1s, and an orbital go up for our sigma star 1s, of what these orbitals look like again. And so what we're looking at for the bonding orbital is the 2s electrons are meeting in the center, so our electrons are meeting in the center, our greatest density of finding electrons between the atoms, and this looks kind of like this. And our greatest probability would be between the nuclei. So we have the greatest probability of finding the electron in a 1s orbital between the 2 nuclei. And then if you think of, well, if these two...
I found this on the web.
Okay, thanks, Siri. And so for the anti-bonding orbital, think of where, if these 2 electrons are meeting in the center, the other 2 electrons are probably going to want to be on the outside of the atom. So the anti-bonding orbital probably looks something more like this, where the greatest probability of finding the electrons is far away from the nuclei. And so this is the idea that we're making the bond, putting electrons between the nuclei, and then the anti-bonding orbital is breaking the bond, putting electrons far away from the nuclei. And so if you imagine here, the p orbitals are doing the same thing. We have the bonding contribution going down, then the anti-bonding contribution going up, and this is the electron density being far away from the nucleus, and this is the electron density being between the nucleus. So we have our bonding orbital, and then our anti-bonding orbital. And the same thing with the p orbitals that are vertical. Now we get our bonding contribution where we go down in energy. Looks kind of funny, but it's just the p orbitals meeting in the center, above and below. So we have the orbitals making their bonding contribution, and then their anti-bonding contribution going upward in energy. And then if you imagine the orbital we didn't sketch on with boron here sticking straight out of the page, would look something like this. And then we'd have the same type of bonding and anti-bonding contribution. And so for our p orbitals, we have bonding here, and then 2 degenerate bonding orbitals for the vertical and sticking straight out of the page orbitals. And so the last thing to think is all of these orbitals on a given atom are arising from the same nucleus. So you're just picturing that you have these orbitals pointing at each other simultaneously from the same nuclei. And again, 3 dimensions makes everything a little bit more complicated, but it sort of gives you the idea, because sometimes you might think, well, why don't we just pick these orbitals up and move them around? Well, we can't move them around. They have to be centered around the nuclei in this particular orientation. Okay, so then from there, the question would be, well, what are the relative energies of these orbitals? And that's where this diagram comes into play here. And then we'll see that for some of the atoms in the second row, this maybe isn't always the case that we go sigma 2s, sigma star 2s. I mean, this is always the case that the sigma 2s, sigma star 2s are the first orbitals. And then these two orbitals here we're going to see vary in energy depending on which of the diatomic molecules in the second row that we're dealing with. But we go from, the sigma and the pi 2p coming next, and then the pi star and the sigma star being the highest energy orbitals. Okay, so let's push past this page onto this page here. This is what's summarizing what these orbital energies look like as we go from lithium-2 on across to beryllium-2. And let's just remind ourselves here too that what we're showing here are valence orbitals. We're not showing the sigma 1s and the sigma 1s star orbitals here. So what we're seeing are the sigma 2s star for lithium-2, and then our valence electrons for each of these molecules that would go into these diagrams. Let's make sure that we're seeing for lithium-2 that we would have a valence electron for each lithium. Beryllium-2 would have 2 valence electrons per atom. Boron-2 would be 6, C2 would be 8, N2, 5 for each nitrogen, so that'd be 10 electrons, 12 for oxygen, 14 for F2, and then 16 for neon-2. And then we have the sigma 2s, the sigma 2s star, and for lithium-2, we're just putting 2 electrons in. We're putting electrons, of course, from low to high energy. And then just like from chapter 6, we have 2 electrons per orbital. And so 4 electrons for beryllium-2. So again, it's a bond order. If we're imagining calculating our bond order here, we'd have a bond order of 1 for lithium-2 that we already calculated, 0 for beryllium-2. And then for boron-2, notice that the next highest set of orbitals, once we go sigma 2s, sigma star 2s, is the pi 2p. And so notice that the pi set of electrons isn't really dependent on the actual nuclei. Like orbital energies usually drop as you go to a larger nuclei. Why might they do that? Our effective charge is increasing from left to right. So as you go from lithium to beryllium to boron, the effective charge is going up. The atoms are becoming smaller. The electrons are closer to that nuclear charge. That makes them more stable, makes them drop in energy. But the pi 2p, I suspect it's because they're just a larger orbital, a little bit further away from the nucleus. They're not as sensitive to the nuclei. Notice that the pi 2p set of electrons aren't as sensitive to the change of nuclei. They're relatively consistent from left to right here. And then for boron, the next orbital we see here is that pi 2p set. And so this is a bonding orbital, and then it's a pi bonding orbital, and I have to follow Hund's rule, maximize the spin of the 2 electrons going into degenerate orbitals, degenerate meaning equal energy orbitals, and so I end up with 2 unpaired electrons. And so if I think about my bond order here, my bonding electrons are 4. So let me shade in red here. The bonding electrons are these and those, and then my anti-bonding electrons are these because they're in the star orbital. And so 4 minus 2 would be equal to 1. So B2 would be best described as having a single bond. And then if we're thinking para versus diamagnetic, for lithium-2, all the electrons are spin paired, it's diamagnetic. Beryllium-2 is diamagnetic. But do you see how boron-2, diboron, would have 2 unpaired electrons? It would be paramagnetic. So if we could get a sample of B2, now it's probably not a very stable diatomic molecule. I'm not entirely sure if you could even have it as a stable molecule, but if we could, it should be drawn into a magnetic field. All right, let's push past C2. So C2, we're putting 8 electrons in. It's just 2, 4, 6, and then 8 electrons. So now we go back to having a diamagnetic molecule. And then C2, it's actually kind of interesting. If you go back to our rules for Lewis structures, remember for diatomic molecules, we said that we should try to satisfy the octet rule when possible. If we want to satisfy the octet rule, do you see how we'd go with this Lewis structure for C2? Because each carbon has 4 valence electrons. And if we want to give each carbon 8 electrons, we'd go with a quadruple bond. But you can see here that according to molecular orbital theory, C2 would probably be better described as having a double bond. A double bond because we have a sigma, sigma star. So our bond order here would be a half, and then we have a total of 6 bonding electrons minus 2 anti-bonding electrons for 6 minus 2. So that should be a double bond. So now the effect of a bonding pair of electrons with an anti-bonding electrons, the net average of making a bond and breaking a bond are lone pairs. And so these two electrons here would probably be best described as being these lone pairs on carbon, and then the net two bonds we have here would be the double bonds from these pi electrons here. Interestingly, C2 would have two pi bonds. Like, this is a weird molecule. I don't think we would ever ask this, and it's a pretty deep question. Be a good essay question on, why most double bonds are described as being a sigma and a pi, from what we saw from valence bond theory. What we see here, the net bonding electrons are actually the two pi bonds. And so C2 would be best described as having a double bond between the two carbons, and then the two bonds being more representative as being pi bonds. Now, this is a very interesting topic because the problem with carbon, if you think about carbon, it has electrons from the 2s orbitals between the nuclei, and then the atoms aren't particularly highly charged. Carbon's not very electronegative. It's still relatively large from left to right. And so if you're a carbon thinking, do I want to put two electrons here in p orbitals where there's already electrons in the way, or do I want to use these bigger p orbitals? And carbon says, let's not use these orbitals. Let's use the space above and in front of the s orbitals. So that's kind of the choice that the molecule is making, is what space do we want to use around the molecule? For dicarbon, we'd be using the pi orbitals to make its bonds. And one of the things with, in the conversation of models, this model here is actually quite accurate for C2 and for these molecules. So when we go from a Lewis structure to valence bond theory, that sometimes those theories get some structures wrong. And here with MO theory, we're usually getting structures a little bit more accurately described. Okay, so let's go from N2. So we're just putting 10 electrons in from 2, 4, 6, 8, and then 10. And so N2 is a pretty happy molecule for a lot of reasons. One is we've just kind of filled up the orbitals in a way that we can make the most bonding electrons possible, the most net bonding electrons, because we have a total of 8 bonding electrons and 2 anti-bonding electrons. And so this is the most bonds we could have for a diatomic molecule. So we have a half, 8 bonding minus 2 anti-bonding for 3. So according to MO theory, we'd never get a quadruple bond for molecules in the quote-unquote main group, so the 2s2p block, the 3s3p block. We'd only be limited to a triple bond. And that's also exactly what we would expect for nitrogen, that we'd expect it to be a triple, and that's exactly what it is. And then the triples, a sigma and 2 pi bonds on from this picture. We get a diamagnetic molecule, all spin paired, so that's good. That gives us the expected magnetic property for N2. And so our bond order here triple, that also matches our Lewis structure that we would have expected. So N2, we're getting a consistent model. And then maybe we're also seeing that the lone pairs are the bond being canceled by the anti-bond. And so for now O2, and this is kind of like the point of it, right, is hopefully this model shows us where we have unpaired electrons for O2. And so we go 2, 4, 6, 8, 10. We have to put 12 electrons in, so the next 2 have to go into that pi star 2p set of orbitals. And so the pi star 2p, 2 degenerate orbitals, so I have to put electrons into the 2 orbitals and spin pair them. And so this is why oxygen ends up having 2 unpaired electrons, is because of these 2 electrons here. And so oxygen should be predicted according to MO theory to be, as it is, paramagnetic, so we get the magnetic property correct for oxygen. And then our net bond order, if we're thinking oxygen from its Lewis structure, we do get a double bond because it should be a half and then 8 bonding electrons minus 4 anti-bonding. So a double bond for O2 was correct. And it's just really the effect of the bonding versus the anti-bonding electrons is where you get the unpaired. And so I've kind of always struggled for a way to sketch this that makes the most sense. But for oxygen, it's sort of like you have maybe something like this, where you have electrons, something like this, we end up with net electron spin unpaired. So I don't know if we'll actually sketch it again like this, but that's sort of the idea of MO theory, is that you have the like sigma 2s star electrons, and then the pi versus the pi star, it's like you had 2 spin paired pies and then 2 unspin paired pies. And so it's really kind of confusing on how you might end up with this picture here, but the key is just ending up with 2 unpaired electrons total. And not 4, not 0, but 2 specifically. And so we end up with 2 unpaired electrons for oxygen within this diagram. Now, one little thing happens here, and we'll show you in a separate diagram that you'll get with your exams to know that this isn't exactly something you have to memorize, but if you notice the sigma 2p set of orbitals starts to go below the pi 2p set of orbitals for O2, F2, neon 2. And so we'll talk about this again in a minute, but on how this isn't something you have to memorize. And the base kind of diagrams of these molecules is also not entirely intuitive. Like sometimes I've seen teachers in the past that I've had that kind of make it seem like, oh, you can predict these orbital energies and the order of them. And I'm kind of like, I don't know, I can't do semi-empirical calculations in my head that involve lots of integration, you know. So somebody had to figure out these orbital energies either through experiments or through theoretical calculations. So we're going to show you in a minute that you don't have to have these diagrams kind of memorized in the orbital energies, but we're just going to have to kind of figure out what orbitals go with which set of energies, and I'll show you the base diagrams you get with your exams on the next slide. But let's just finish off F2 to neon 2. So F2, we're just going 14 electrons in, so 2, 4, 6, 8, 10, 12, 14. So neon 2, or excuse me, fluorine is just finishing off the pi 2p star set of orbitals. And so the net bond order here is exactly as we'd expect for F2 for single, a half, 8 bonding, 6 anti-bonding for a single bond. All the electrons spin paired, so diamagnetic. And then F2 would just look like we expect a single bond between the fluorines, lone pairs all the way around. And so we just have the effect of bonding, anti-bonding, pi bonding, anti-bonding, the other pi bonding, anti-bonding. Sort of the idea of where these lone pairs are coming from in our Lewis structure. And probably not too surprising that neon 2 is not going to be too happy because we fill in all of our electrons. So that's 14 and then 16 electrons for neon 2. So we go back to neon 2 having no net bond order. So our bond order for neon 2 would be 0. So we wouldn't expect 2 neons to bond with each other according to MO theory, and they don't bond with each other, so that's a good prediction. And then if they did, we'd expect it to be diamagnetic, so there wouldn't be any unpaired electrons here if this molecule did form somehow, and so that would be neon 2. Okay, so let's try to take a look at the diagrams you get with your exams and like how to piece this together and what type of questions you might see on exams on this topic. Well, actually, before I show you the actual diagrams you get with your exam, this is the table from the book, just kind of showing for B2, C2, N2, the same set of orbital relative energies that we saw before. So the sigma 2s, sigma star 2s, and the pi set of orbitals comes next. You can always pick up the pi orbitals because they're the ones that are doubly degenerate. There's 2 that are equal in energy. And then we have the sigma 2p orbital next. And then notice you have this orbital switch here, that the sigma 2p is the more stable orbital. So we go sigma 2s, sigma star 2s, then sigma 2p, and then the doubly degenerate pi 2p next. And so then the bond orders are exactly as what we were expecting before. So just a summary here of bond order from 1 to 2 to 3, and then back to 2 to 1 to 0 for O2, F2 to neon 2. Let's think bond orders real quick. Let's get a little comparison between a few molecules here and how we can compare their bond orders. And so let's look at O2 versus F2 first. So O2 is a double bond. Remember we say double bonds are shorter than single. So O2 with 2 bonding pairs of electrons ends up having a shorter bond. So 1.21 angstrom versus 1.43 angstrom for F2. So having a double bond holds the electrons closer together. So a double bond is shorter than a single bond. And so then, of course, a triple bond should be even shorter. So let's look at the bond length of N2, triple bond. So 1.1 angstrom, certainly less than 1.21 angstrom. So we see here that N2 has a shorter bond than O2, which is shorter than F2, and that's just based on their bond type. And then you can also see the reversion of their bond strength, that the triple bond should be the strongest. So N2 is strongest O2 in the middle, F2 the weakest bond here in terms of strength. So if we want to break the bond, triple bond is going to be stronger. So 941 kJs per mole for our bond enthalpy for N2. And then O2 is weaker and F2 a lot weaker, being a single bond. And now there's two molecules on this chart that are equal in bond order. So if we were to compare C2 versus O2, we can make a comparison here too. Because when we're comparing C2, it has a double bond, O2 has a double bond. Well, which atom's smaller? So if we're comparing O double bond versus C double bond, which atom is just smaller from periodic trends from chapter 7? Oxygen's smaller because from left to right size decreases. And so the O2 bond should be shorter than the C2 bond. And that's going to make the O2 bond stronger. And well, actually, let's take that back for a minute. So for the bond enthalpy, C2 ends up being stronger. But I think there's more to the double bond strength here than what meets the eye. So the bond strength is a little bit harder to compare, but the bond length is easy to compare just off of size. So this trend here is being made because oxygen is simply smaller than carbon. So we can compare bond lengths that have the same type, just based on atom size. So if you want to compare two single bonds, or two double bonds, or two triple bonds, you just look at the atoms in the bond and ask the question, which atom is smaller versus bigger than the other? If you have a single bond versus a double bond, the single bond is just longer than the double. And this is so long as you're in the same row of the periodic table. So any single bond in the second row will be longer than any double bond from atoms in the second row of the periodic table. If we start comparing double bonds in the second row with single bonds in the row above it, you get a break in the comparison. So you want to compare atoms in the same row of the periodic table with each other. And so the last set of atoms that have the same bond order that we can compare bond lengths for would be B2 versus F2, because they both have single bonds. And so for boron, boron's bigger, has a longer bond than F2. And so here, just again, it's boron from left to right is bigger than fluorine, so the B2 bond single is bigger, longer than the F2 single bond. Okay, so this is just reminding us here that diamagnetism is a result of all electrons in every orbital being spin paired. These substances are actually weakly repelled by a magnetic field. They're certainly not pulled into the field. They're actually weakly repelled by the magnetic field. That's just from all the spin of the electrons creating a repulsion with the magnetic field. It's just a weak repulsion, though. The substances with net spin, it's that net spin of the molecule that's pulling those substances into a magnetic field. So the presence of one or more unpaired electrons terms a substance to be paramagnetic. And so is O2 paradiamagnetic? And of course, we saw from inspection of its diagram that it's paramagnetic. And so this is getting towards a diagram. So like this picture here, these pictures are what you get with your exams. And so the idea here would be for B2, C2, N2, and any ions that are comprised of those atoms, we would use a diagram set that looks like this set here. And then we'd have to simply know that this would correspond to this sigma 2s, this would correspond to the sigma star 2s, this would correspond to the pi 2p, because there's two, that's how I know it's the pi's, there's two orbitals here. The one set of orbitals would be the sigma 2p, and then we have our anti-bonding orbitals going up, our sigma star 2p, or excuse me, I wrote pi, I said sigma. The pi star 2p, it's pi because there's two, and then sigma 2p star, the anti-bonding 2p set. Now, it might litter the diagram a little bit on what these orbitals look like, but our sigma 2s, this should just look like our nuclei kind of like this, our greatest shading in the middle. The sigma star 2s should look like the greatest shading away from the nuclei. So our greatest shading over here, something like this. Our sigma 2p orbital, let's do the sigma 2p first. So let's do this orbital here. This would look like this orbital here, our nuclei in the middle, our greatest probability between the nuclei. You'd see something that looked like a p orbital though. So you'd expect two p orbitals overlapping like this. and then we'd see a bigger orbital in the middle, so the result would look something like small orbital, big orbital, small orbital here with the nuclei in the middle. So that would be our sigma 2p. The anti-bonding orbital of that, so the sigma star 2p, would just look like the bigger orbital on the outside, smaller orbitals in the middle, nuclei in the middle. So we'd have our electrons far away from the nuclei here. Again, symmetrical about the bond axis, so that's our sigma star 2p. And then our pi 2p set are the ones that would look like the kind of nuclei here, having the electrons here and there, and then the opposite sticking straight out of the page. Can't really sketch it with shading, but with shading you can show it a little bit more easily. So you just have the vertical and then the sticking straight out of the page set of orbitals look like that. And then the anti-bonding pi 2p set would just kind of look like our nuclei, where the p orbitals are just bending away from each other, almost kind of like a butterfly or something, where the p orbitals are trying to bend themselves away from each other. The idea is electrons in the middle for the bonding orbitals, the other electrons far away from the nuclei. And so the pi orbitals, these are planar orbitals, so the orbitals should look like a plane. A sigma orbital should be symmetrical about the bond axis. Okay, so we see B2, C2, N2. The only difference for O2, F2, neon 2 is just this orbital here is lower in energy, so we go sigma 2s, sigma star 2s in terms of our relative energy. Then sigma star 2s, or excuse me, screwed both of them up. It's sigma 2p. Why is it sigma 2p? Well, it's the sigma orbital from the 2p set of orbitals. So these are 2s's because they're the bonding, anti-bonding from the 2s orbitals of the atom, and then these are the 2p set. So our sigma orbital from them is a sigma 2p. Then we go pi 2p, and then pi star 2p, and then sigma star 2p. So it's just sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p, sigma star 2p. So pi, there's two orbitals. They're the planar orbitals, sigma, the bond symmetric orbitals. And so these diagrams here, it's just interpreting which orbital is which, maybe what shape goes with each orbital, and then how we fill electrons in from low to high energy. So energy is increasing towards the top of the diagram. So if we want to fill in the diagram for C2, 2 minus, this is a valence orbital diagram, so I count my valence electrons here. For C2, 2 minus would be 2 times 4 for the 2 carbons, and then plus 2 for the charge. That gives me 10 electrons going into the diagram. So over here on my diagram, C2, 2 minus is in the middle. The atoms on the outside, those are the atomic orbitals of C2 minus and C2 minus being brought together. I don't necessarily need to put these electrons in here, but I could. This might help you picture what we're doing here is bringing C minus on one side, C minus on the other, just in terms of their relative energies, and allowing these orbitals to interact with each other. So C minus and C minus added together would be C2, 2 minus. So C2, 2 minus are described by the orbitals in the middle. Just making sure that we see that this is sort of one of the atoms, and then this is the other atom. And they're, the idea of them both here, you can imagine the orbitals overlap with each other. Just imagine the s orbitals overlap, so we get our bonding orbitals going up and down. And then imagine the 2p orbitals overlap, and then the pi orbitals overlap. So we get our pi, and then our sigma, and then our sigma. So we can get the diagram too from scratch, but just kind of like, and I'm just trying to think here again, the p orbital's horizontal, p orbital's vertical. I get the doubly degenerate for the vertical and sticking straight out of the page. And so to put 10 electrons in here, just 2, 4, 6, 8, and then 10. I didn't necessarily need to fill in all the symbols and draw all the pictures to do this question. I was just trying to be kind of how might I interpret a diagram if I need to, what would I expect you guys to know and to be able to fill in. For this question here, if I just like erased everything and then just put 10 electrons in, then I'm just really just making sure that we know that these are the bonding orbitals And just this one orbital here is antibonding. And it's antibonding because it goes up relative to its atomic orbital set. So this is antibonding because it just goes up relative to the 2s orbitals that it's comprised of. And so my bond order for C2 would be a half, and I have 8 bonding electrons and then 2 antibonding. So my bond order is 3. And then the molecule has all of its electrons spin paired, so it should be diamagnetic. So this question here again was just saying, for C2 what's its bond order? What's its magnetic property? Is it paramagnetic or diamagnetic? And what's its bond order? So here we see bond order is 3, and the molecule has all of its electrons spin paired for a diamagnetic molecule. So predicting magnetic properties, predicting bond orders, maybe like imagining that a structure like this with a triple bond, 2 lone pairs, that this is what C2 would look like. And the minus charges are just the formal charge we would expect. So this is carbide ions. This is actually the ion that we were seeing react with water to produce, this reacts with water to produce acetylene, then we ignited it in the pumpkin last Monday. So this was the reaction that was leading to acetylene from carbide ion. So carbide is C2 Okay, so bond orders, magnetic properties, and maybe comparing bond lengths of different molecules from their MO diagram are some things that we can do with MO theory. So let's see here. So it says, what about O2 with a minus charge? And so that's superoxide. So we learned how to name O2 back in chapter 2. So this is superoxide. So what does its MO diagram look like? Well, I just use the diagram for O2, F2, neon 2, and any ions comprised of those atoms. And so we go, and then we might count the electrons, 2 times 6 for oxygen, plus 1 for the minus charge, that's 13 electrons. And so 13 electrons in, 2, 4, 6, 8, 10, 12, 13. So for O2 again, if I want to label the orbitals, and really, I just really want to make sure I get the antibonding versus the bonding. So I have the sigma 2p, the pi 2p, and then the pi star 2p going up in energy, and the sigma star 2p unfilled. So my antibonding electrons are these ones here, and then my bonding electrons are these 8 electrons. And so my bond order is a half. I have 8 bonding electrons, and then minus the 5 antibonding. So I end up with a 3/2 bond order. It doesn't ask it, but this would be paramagnetic, because all it takes is 1 unpaired electron, so this molecule here would be paramagnetic. Be drawn into a magnetic field. Now, I like the question. It's kind of a weird question put in a multiple choice test, but like, what does this look like? What would its Lewis structure look like that's consistent with this MO diagram? Well, let's actually start with 2 oxygens. Let's in fact go back to the Lewis structure we had or would have predicted. I think we'd predict a Lewis structure like this from our chapter. We'd leave one of the oxygens deficient of an octet, and so we'd have this oxygen here with a 0 charge, this oxygen here with a minus charge. This would probably be like our best Lewis structure from chapter 8 that we'd come up with for a molecule with an odd count. Remember, an odd count, or like which atom do you leave deficient of an octet? Well, if you imagine the bonding, anti-bonding, so if we just imagine that we have 2 oxygens, we have our bonding and anti-bonding electrons, we have at least a net bond somewhere between the molecules. And then we have a pi and a pi star anti-bonding set of orbitals. So we have those two like electrons. If I'm just like canceling these out here, I have like the net bonds here, bonding, antibonding, bonding, antibonding here. I have like a net bond here, so maybe this is my single bond that I've drawn so far. And then somehow I end up with electrons like here and here that are spin paired. And then I have one electron in the middle that's like spin unpaired. And so that should be the right count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I have 13 electrons per O. And then if I count electrons total around each of the O's, if we imagine like the octet, we have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 electrons for each O in this structure with like a fractional bond order. And so this like Lewis structure actually makes a lot of sense, I think. We have a net bond order of 3 halves. We have each oxygen somehow satisfying the octet rule, even with an odd count of electrons. And then the formal charge in each O kind of goes back almost to the prediction from oxidation numbers. Each oxygen's charge would be -1/2. Now, how do I know it's -1/2? Well, all I know is that they have to be the same. The total charge is -1. So I'm just kind of going back to the sort of idea. If the net charge of the thing's -1, and each of the O's are identical, then each of the O's have to be -1/2. If I wanted to calculate, I don't know if that would be easy to calculate the actual charge in each of the O's, but this is just really to show you that a fractional bond order here really allows each oxygen to simultaneously satisfy the octet rule. So this Lewis structure actually makes a fair bit of sense, even though it might have been hard for us to piece together without seeing MO theory first. So we're just kind of seeing the effect of lone pairs from bonding, antibonding, canceling each other out, and then the net bond order for the electrons that should be net between the atoms. So our net bond here, order of 3 halves for O2 with a minus charge. Now, what if I had like O2 with a positive charge? So what if we said, what about O2 with a positive charge? So the key here would be that we still would do 2 times 6, but then we have to subtract an electron for the positive charge. So we'd have 11 electrons. Then we'd have our base diagram that we're just plugging into here. And we're just putting 11 electrons in. So 2, 4, 6, 8, 10, and then 11. So O2 with a positive charge would have 1 unpaired electron, would be paramagnetic, and the bond order would be a half, and then 8 bonding minus 3 antibonding for 5 halves. So we'd have just something that looks like this. Something like that. I don't know. The Lewis structure is not a big detail. Lewis structure here is just kind of trying to tie it all together so I can see a net bond order that's fractional. So I can have 5 electrons being shared. I can have 8 electrons still around each O. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons total for the molecule. So if we're ranking the bond lengths of O2 plus, if we said rank O2 minus, O2, O2 plus by increasing bond length, like which of those bonds is the longest? Would be O2 minus because it had the least bond. And then O2 in the middle, and then O2 with a positive charge would probably be the shortest, and this is just by bond order. So we had 5 halves versus 2 versus 3 halves. So single longer, double shorter, triple even shorter, and by fractions we can go, of course, in the middle. So 1.5 bond should be longer than a double bond, longer than a 2.5 bond. Okay, so the very last slide from chapter 9 is just, well, what do you do when you have 2 different atoms bonded together, like N and O, for a diatomic molecule? And so we'd seen this previously, if you recall. We were weighing before for the Lewis structure. Do we go with this Lewis structure, or do we go with this Lewis structure? Well, we talked about this in chapter 8 for diatomic molecules, we were saying, well, you have a fraction, you have 5 plus 6 electrons for 11 total electrons. So which structure do you go with? And we were like, well, this one's bad because it puts a plus and a minus on O and N. This one's good because it puts 0 formal charges, so we went with this Lewis structure for NO, if you recall. And so now with MO theory, we can be a little bit smarter and just try to put the electrons in an order. We use the base diagram for the more electronegative atom. Like, we tend not to ask about this. I wouldn't be too concerned about having to put a diagram like this together. But let's just try to interpret the diagram, though. So we go sigma 2s, sigma star 2s, sigma 2p, pi 2p, pi star 2p, sigma star 2p. So the order we would expect for like O2, F2, neon 2, where the sigma 2p is the next higher orbital. And we're just filling 11 electrons in, 2, 4, 6, 8, 10, 11 electrons. And then we end up with the same kind of picture we just saw for O2 plus. So we end up with a structure where the bond order would be equal to a half, 8 bonding, and then only these 3 anti-bonding for a 5/2 bond. And so like NO is actually better described not really through either of those 2 Lewis structures, but really through one that has a bond order of 5/2. So something more like we just saw on the previous page. Something more like this, where we're going to have a 5/2 bond here, and that allows each atom here to satisfy the octet rule. We could imagine oxygen is more electronegative. Oxygen smaller, more positive, more electronegative. That's why the orbital set for O is a little bit lower than for N. So notice that the orbital set for oxygen is a little bit lower in energy than it is for N. And then we can still imagine the bond should be polarized. Oxygen should still pick up some negative charge. So the bonding pair electrons should still be shading more towards O than towards N, so that oxygen should be the negatively charged atom. And so this is how we can kind of put together and understand some what we call heteroatomic diatomic molecules. But you'll see on exams, you'll see in the practice exams that when you see questions on this topic, we ask you about atoms that are the same, so like N2, O2, F2, etc. You can throw charges where you're just adding electrons for anions, taking electrons away for cations, and then you can rank atoms based on bond length, based on their bond type, etc. Okay, so that kind of wraps up chapter 9. From our coverage. We'll see some review questions on MO theory as we get into some review topics into Wednesday. So to kind of wrap class up for today, let's maybe get into a couple of topics that I think are worth talking about today, and then we'll get into some more review topics on Wednesday and into next Monday. I did post just this morning a set of review topics for chapter 7 through 9 that we'll be looking at over the next couple lectures. I wanted to start off with this one here today. There was a question from recitation last week that was getting at the Born-Haber cycle. Now, I don't think there's a whole lot that we necessarily need to know here other than just the whole idea of what a lattice energy is that it's specifically the ionic solid decomposing into its gaseous ions. And that's always going to require energy. It requires energy for an ionic compound to dissociate into its gaseous ions. There's attractive forces holding the ions together. So the lattice energy is kind of a measure of, well, how strongly are those ions attracted together? How much force are they being attracted together by that we have to supply so much energy to break them apart? And so the lattice energy allows us to come up with the idea, if you recall, that if the ions are closer together, if the ions are smaller but with the same charge, the lattice energy is higher. It takes more energy to separate smaller ions and larger ions. And then if the magnitudes of charge are higher, takes more energy to separate. So if you have 2 plus 2 minus ions, those are more attracted together than plus 1 minus 1 ions. This chart here is just kind of showing you, like if you wanted to go from magnesium chloride to try to calculate a lattice energy, what you might say is, well, how much energy does it take to go to its elements, magnesium and chlorine? So you might just say, well, magnesium to its elements, that's usually going to be uphill in energy because compounds are more stable than their elements. So you go uphill to the elements. You use delta HFs to get there. You can quantify this is going from solid to gaseous metal. So we're going from solid magnesium in its usual elemental form to gaseous magnesium. We have to break the bond between the 2 chlorines, the Cl2. That takes energy. We have to ionize magnesium to plus to 2 plus. That takes energy, takes even more energy to go from magnesium plus to 2 plus than the first ionization energy. We get some energy back when we make Cl minus because electron affinities are often negative. So we get some energy back when we go to Cl minus. We're making 2 of them, so we get the electron affinity of chlorine times 2 back for the 2 chlorines. And then if you wanted to then say, well, these ions being attracted together then goes downhill. This is why ionic compounds actually form is, you can talk about how magnesium's happier, if you will, as magnesium 2 plus because it gives it that noble gas count. But that's not exactly why magnesium chloride forms, because it takes a lot of energy. You see, it takes almost like 3,000 kJs per mole of energy to go to magnesium 2 plus or magnesium. But the key is once you go to magnesium 2 plus, once you give those electrons to chlorine, you get some energy back from Cl minus, you then get the electrostatic force of attraction. So it's like this electrostatic force of attraction is why MgCl2 forms, is because of that lattice energy. And then if we get into a topic that you'll see in if we talk about a topic you'll talk about chapter 13 in Chem 1220, like why do compounds dissolve in water? Well, a compound like magnesium chloride would dissolve in water if those ionic forces of attractions are met or exceeded by the attraction with water. So if you can have an ion dipole force that's stronger in collectiveness than the ionic bonds were, then a compound can dissolve in water. So you can gain an appreciation that compounds that have really strong ionic forces of attraction probably aren't going to easily dissolve in water. And so, like things that dissolve in water are actually usually smaller. So like you get stronger ion dipole forces when ions are smaller. That's a really interesting property that we see with lattice energy is being smaller is better. Like having the plus minus on smaller ions makes them harder to separate than if they're more massive ions. More massive ions, weaker attraction, they're further away. Like imagine you have a plus ion here and 2 miles down the road you have the minus ion. There's like no attraction there. But if they're like right on top of each other, much stronger attraction, harder to separate. So the Born-Haber cycle, I wouldn't expect that you'd have to put together like a cycle like that to calculate a lattice energy, but I think understanding it helps you appreciate why lattice energies are positive, but why that lattice energy is important for the formation of ionic compounds. So for this question here, some of these are just old exam questions, and a lot of them are the ones that were kind of tricky. So like this question here is asking which of the following has resonance structures. So when you see a question like this, what you're trying to picture is for the ions that are shown, can you sketch an equivalent yet different Lewis structure? Is there some way to sketch a Lewis structure of compound 1 that equivalently represents the same collection of atoms and bonds, but in a different order? And there's no way that we can do that for compound 1. Like that's the only possible structure for compound 1. You can't move those electrons around, but you can in 2. If you look at 2, I can take these electrons here, move them to here, move this bond over to here, and move this set of electrons over to here. And if I do so, I come up with this Lewis structure that looks like this. And do you see how that's the equivalent Lewis structure is 2, but it's different. It's different in which atom's making the CO double bond. It's different in which carbons are making the CC double bond. If we were to look at this structure here, the real structure should look like this, where these bonds here are like a 3/2 order. The 2 O's are double or single, they're 3/2 as well. Like these, the CO bond here would have the same length as this CO bond. The 2 carbon-carbon bonds would be equal in length. You'd have the effective resonance going on. You'd have the compositing or averaging out of the structure and something like 2. And so compound 2 would look nothing like A, nothing like B. It wouldn't be going back and forth at all times. It would look like the composite, like this structure over here. And so compound 2 definitely has resonance going on. Compound 3, there's no, like imagine what we're asking is there's some other Lewis structure that you can sketch that looks the same but is different. And we can't do that for 3. And then for 4, maybe it looks like we can, but we can't. Like, is there some way to move this electron pair over to here? There isn't, because you'd have to like break a covalent bond and move a covalent bond. We're not moving bonds, you're only moving electrons through resonance. So we can't do that with this structure either. So only 2 here exhibits the effect of resonance. Okay, so just a couple of review questions into this packet. We'll look at the others, or start with the remaining questions on Wednesday and get into the rest of those on next Monday. All right, guys, thanks for your attention today. See you on Wednesday.